The James Webb Space Telescope has just captured something truly extraordinary, what appears to be the final moments of the star Betelgeuse. After months of careful and silent observation, Webb recorded the beginning of the star's collapse, a moment scientists have long theorized about but never witnessed in real time. Betelgeuse, a red supergiant located just 642 light-years from Earth, is now in the midst of a spectacular explosion. Unlike past detections of distant supernovae, this is unfolding in our cosmic neighborhood, and we're watching it happen live. What Webb observed was nothing short of revolutionary. Massive shockwaves are tearing through the star's outer layers, while jets of plasma shoot into space. The gravitational impact is so intense that it may be distorting the very fabric of spacetime. For the first time, instruments are delivering direct, unfiltered data, not theoretical models of a star imploding. Webb has mapped enormous convective bubbles erupting from Betelgeuse's surface, traced plumes of hot gas dispersing into the void, and detected energy signatures from a collapse so violent that it's forcing scientists to rethink our understanding of supernova mechanics. Betelgeuse, one of the brightest and most recognizable stars in Orion, has long intrigued astronomers, but now it's become more than a red giant. It's a real-time case study in stellar death. Webb has detected rare elements like technetium and yttrium forming in the explosion, materials synthesized only during the final moments of massive stars. These elements are not just curiosities. They're part of the very matter that composes planets, life, and even our own bodies. This explosion is not merely a cosmic spectacle. It mirrors the very process that once seeded Earth itself. Webb's data suggests that the universe doesn't simply burn out. It recycles. As Betelgeuse sheds its outer layers, a glowing halo of dust and gas forms around it. Webb's instruments reveal that hot waves of gas are disturbing nearby interstellar clouds, altering the chemical composition of the surrounding space. There's even the possibility that gravitational waves were released during the collapse, ripples in spacetime itself. If confirmed, it would be the first time a visible supernova has been directly linked to a measurable gravitational event. But perhaps the strangest twist is that Betelgeuse's core isn't collapsing symmetrically. Webb has detected signs of fallback, where some of the ejected material is being pulled back inward. Magnetic fields are generating chaotic voids and erratic plasma flows. Some astrophysicists believe we may be witnessing the birth of a transitional object, possibly something between a neutron star and a black hole. Though the idea remains controversial, Webb's data makes it a possibility that can no longer be dismissed. Naturally, people wonder, are we in danger? Fortunately, the answer is no. Betelgeuse is distant enough that its radiation poses no threat to Earth. However, its explosion could still affect our region of the galaxy. Gamma rays, optical fluctuations, and high-energy particles might influence nearby gas clouds or subtly affect how starlight reaches us. Webb is monitoring every wavefront, measuring their velocity and intensity, giving humanity a front-row seat to one of the universe's most powerful and transformative events. This moment provides invaluable insight into how stars evolve, how galaxies are born, and how the elements vital to life are forged. It's one thing to build theories, but another entirely to observe the process in real time. We now have a direct view of how a star's death can ignite cosmic rebirth. As Betelgeuse fades from Orion's shoulder, it's leaving behind an expanding nebula, a colorful, luminous cloud of debris and energy marking the grave of a stellar giant. Webb's observations affirm that stellar endings are not conclusions, but transformations. The death of Betelgeuse is creating the building blocks for future stars, planets, and possibly even life. In the remains of the explosion, Webb has detected traces of rare materials like aluminum-26 and iron-60, radioactive isotopes that decay over millions of years. These same isotopes are found in meteorites on Earth and were long believed to originate from a nearby supernova. Now, we're witnessing that process in real time, confirming a theory that may explain how our solar system itself began. More surprisingly, Webb's instruments detected unexpected concentrations of phosphorus, one of the essential elements needed to build DNA. Its early appearance in the ejected material suggests that the ingredients for life may form faster and more often in the galaxy than once believed. If every supernova can seed space with life's building blocks, our universe may be far more biologically fertile than previously imagined. Following the explosion, ground-based telescopes detected a dramatic rise in optical and ultraviolet emissions from Betelgeuse. But it wasn't just brightness, it was structure. The shockwave had collided with older, previously shed material, creating a series of concentric rings. These rings act as time capsules, preserving the star's life history before its death. Each layer reveals information about mass loss, instability, and violent internal eruptions. A detailed autopsy of a dying star, unfolding live. Then, something even stranger happened. Radio telescopes in Chile and South Africa picked up structured low-frequency signals from the region. These weren't alien messages, but likely bursts caused by magnetic field interactions or shockwave collisions, phenomena usually associated with magnetars or hypermagnetic neutron stars. This raises the tantalizing possibility that Betelgeuse may be transforming into one. Gravitational wave detectors like LIGO and Virgo have picked up lopsided wave patterns, suggesting the core remnant isn't a neat, spherical object. If Betelgeuse has become a magnetar or something even more exotic, it would be the closest such object ever studied. Webb hasn't only focused on the core. It's documenting how Betelgeuse's explosion is altering the surrounding space. Previously calm dust clouds in Orion are shifting. Some are becoming ionized, while others are stirred into motion by radiation pressure. The Atacama Large Millimeter/Submillimeter Array, ALMA, has even confirmed the formation of new star-forming clumps just outside the debris field. Betelgeuse's death is quite literally giving birth to new stars, and Webb is capturing the process down to the molecular level. Even the Hubble Space Telescope, though less advanced than Webb, has contributed by tracking the shockwave in ultraviolet, aiding the construction of 3D models of the explosion and helping researchers understand how various wavelengths of light interact with the expanding cloud. Soon, Webb will narrow its focus on the core in an attempt to determine what exactly has formed. A neutron star, a black hole, or perhaps something never seen before. What makes this event especially poignant is its cultural and historical significance. Betelgeuse has been a fixture in the night sky for millennia. From ancient Egyptian mythology to Polynesian navigators, it served as a celestial reference point, a cosmic constant. Now, that familiar star is fading. Future generations may never see Betelgeuse as we did. Instead, they will see a nebula, a vivid monument to the transformation of something ancient and brilliant. In these final days of Betelgeuse, Webb has given us more than just scientific observations, it has given us perspective. This cosmic event is a mirror, reflecting the impermanence of all things and the universe's astonishing capacity to renew itself. From the dust of a dying star, new worlds may emerge. Every atom in our bodies was once part of a similar collapse, some ancient supernova's last cry into the void. Yet the story is far from over. Webb's latest data reveals subtle flickering pulses at the heart of the expanding cloud, possible signs of a newborn neutron star. If confirmed, these pulses would mark the formation of one of the most extreme known objects. A neutron star is so dense it compresses the mass of our sun into a sphere only a few kilometers wide. It spins rapidly, emitting radiation in pulses like a cosmic lighthouse. This may be exactly what Webb has discovered, the birth of the nearest pulsar ever observed. Radio observatories worldwide are scanning for repeating pulses to confirm its identity. Meanwhile, Webb's infrared instruments have detected a fast-spinning torus, a ring of gas circling the core. This was unexpected, especially so early, and suggests that the star collapsed asymmetrically, ejecting material along its equator. This signature is often associated with stars massive enough to eventually become black holes, depending on their remaining mass and spin. Webb continues its search for evidence of a forming black hole. If one has emerged, it may be hidden behind dense clouds of dust, quietly feeding on leftover material and generating faint X-ray emissions. Future missions like NASA's upcoming Lynx Observatory could provide the tools needed to answer that question. In the meantime, Webb keeps uncovering new molecules in the cooling debris, carbon chains, sulfur compounds, silicon-based clusters, all the ingredients necessary for planet formation. What was once believed to take centuries is now occurring in a matter of months. The sheer speed of this transformation hints that the creation of habitable worlds may unfold far more rapidly than scientists ever imagined. It's a profound cosmic truth. Destruction is often the first step toward new creation.